Good morning, guys. First thing, before we begin doing anything to do with science, hope you're all staying safe, hope you're all staying healthy, hope you're staying at home, just making sure you're not out of this mess, just making sure we do our part. Now, how we're going to do this in class. What I'm going to do is I'm going to give you one topic per week with one assignment. We have a couple things left to do in chemistry. Today we're going to go over kinetic molecular theory and ideal gases. We're going to talk about, with those guys, we're going to talk about pressure, volume, temperature, and we're going to talk about that gas and its equation, PV equals nRT. So a lot of it has to do with pressure, volume, and temperature. Those are our three main things that we're going to look at as we go through this. So just kind of bear with me on this. I know this is something new, something that we haven't had to do in the past, something that it's all a new learning curve for you, for me, for everybody, so don't feel overwhelmed as we begin to do this. Now, kinetic molecular theory, so let's just jump right into it. Kinetic molecular theory here of matter with 5.1. We're talking about the four states of matter. We got solid, liquid, gas, and a plasma. Now, with the kinetic molecular theory, with the solids, the four states of matter, we know how these things work. We've talked about these in class previously. A solid, we know that those molecules are tightly packed, but yet they're still moving. We know a liquid here, those guys are sliding past one another in their state of matter. In a gas, we know they're random. In a plasma, we know the protons and the electrons have separated from one another, and we know that plasma makes up 99% of all of our states of matter in the universe, but yet we find it very little here on Earth. One place you do find it is like in the lights above my head right here, say the fluorescent lights, so that's one place you can find it. The next thing, four states of matter, we know we can see each one of them in this except for plasma. For each one of these, it's just a solid, a liquid, and a gas. In this picture, our solid here is the ice. We see we can have water. Water here in its liquid form, water here in its gaseous form, water here in its gaseous form. And in this gaseous form, it can condensate, it can precipitate, it can do all that stuff in the picture in the top left-hand corner. Stuff that's very simple and very easy for us to understand, that we have already seen before. But plasma, our sun is made up of nothing but plasma. So plasma is very hot, and you see it when you see pictures of our universe, when you see these nebulas, all these pretty different colors of pictures that come from outer space. That is plasma that we're seeing. The next thing, with kinetic molecular theory, we know we can go from a solid to a liquid or a liquid to a gas, or we can go from a gas to a liquid and then a liquid back to a solid. So those terms, solid to a liquid, we know that is melting. Liquid to a gas, we know that is evaporating. Gas to a liquid, condensing. Liquid to a solid, solidifying. But we can go straight from a solid straight to a gas, and we call that sublimation, okay? It takes extreme temperature for that to be able to happen. We can also go from gas to a solid. It takes an extreme amount of temperature leaving the system, okay? Because that thing is freezing all of a sudden, and we call that deposition. As we begin to talk about this, we won't bore you on some of the history that goes along with it. But when we do talk about the kinetic molecular theory, it will be based off of absolute zero. We've talked a little bit about absolute zero throughout class. We know we use Fahrenheit. We know most of the world uses Celsius. But the Kelvin scale is what we use in science. That is our unit of measurement that we use most of the time, especially when we deal with ideal gases. Everything will have to be put into Kelvin. And it kind of just gives you this picture gives you a very good idea here. We know water freezes at 32 degrees Fahrenheit, which is 0 degrees Celsius, but that's 273 K. Here, we know at absolute zero, negative 459 degrees Fahrenheit, very cold, obviously. Celsius, negative 273, Kelvin is 0 Kelvin. At 0 Kelvin, everything stops moving. Theoretically, this should not be able to happen, because if you take and you think about the number 1, say we get to 1 Kelvin. When we get to 1 Kelvin, we keep going down. What do we have to do? We half it. So 1 to 0.5. Take half of 0.5, it's 0.25. Take half of 0.25, it's 0.125. Take half of 0.125, it's 0.0625. All right, so the number keeps going down, right? It keeps splitting in half. So therefore, technically, that is another number that is considered to be infinite. All right. We keep going. Some of the stuff you guys will see in chemistry. Now, this chart is very, very important. If it were me, I would pause the video at this point and I would make this chart. I would write this chart down if it were me, and I were beginning to think about the states of matter and how they work. But we can talk about it just a little bit here. Solids, liquids, and gases. So we talk about, let me close this window over here so there's a glare maybe on the TV. Attractive forces, okay? The attractive forces of a solid are very strong. They're held tightly together, just like we see. That's why we can see solids. Liquids, they're moderate. Gases, none. That's why we can't see the gases in this room, because there's no attractive force holding those guys together. Molecular packing. Obviously, we said a while ago that solids are tightly packed. They vibrate off one another. Liquids, they slide past one another. Gases, 99% empty space. Again, we can't see them in this room. Molecular motion, they vibrate or spin in place. Liquids slide past. Gases are random. The shape of matter. We know that solids have a definite shape, and we know they have a definite volume. Okay? We know that liquids have an indefinite shape, because we can pour it on the ground, it just goes wherever it wants to, but it does have a definite volume. And then we know gases are both indefinite. Alright, indefinite shape and indefinite volume. We will talk about compressibility. Can I compress it? A solid, I can't take this desk and compress it down anymore without heating it up or without breaking it. So it's not able to be compressed. A liquid, same thing. They're incompressible, but I can take the gases in this room and I can compress those gases down into a certain size, into a, say we put it into a bottle. Okay, so we can compress those. Their matter, definite on all three. And then the flow. Do they flow? Okay, solids, we know they can't flow. Liquids, they do flow. They flow past one another. And then gases, yes, they flow also. We'll talk about expansion. You see here with expansion, we see a hot air balloon. Okay, we know that a hot air balloon works by us pumping in the heat. The heat creates the carbon dioxide. Carbon dioxide is what makes that balloon expand. It's what makes that balloon go. So therefore, when that happens, the pressure goes up inside of the balloon. Alright, so as the pressure goes up, that means the temperature had to go up. If the temperature falls, okay, think about the balloon. Think about a helium balloon at home. Or just anything. Think about a bottle. Okay, if we heat a bottle up, the pressure inside that bottle begins to expand. Okay, if we cool it down, the bottle begins to shrink. So that is expansion. The next thing is fluidity. Solids, liquids, and gases. A gas here, all right? Are they fluid or not? Are they flowing? Obviously, a while ago we said a gas does not flow. A gas does flow. Liquids flow. Solids vibrate. You also think about down here at the bottom, kinetic energy. We've talked about kinetic energy. How kinetic energy is energy that is moving. Solids, low kinetic energy. Gas, the higher the kinetic energy because they're moving more. The next thing is density. Density here says the density of the gases depends on the temperature. The higher the temperature, the lower the density. Therefore, warm gases rise and the cool ones fall. Compression. You think about compressing. Compression here. When we think about compression, we give you an idea here with a spring. A spring is unloaded. A spring is not pressed together. It's not compressed. This right here would be our solids. I can't compress it. Here, I can compress that spring, which would be our gases and our liquids. We can compress those. And then diffusion. We know diffusion is going from a low concentration, or from a high concentration to a low concentration, so it diffuses out. If you were in this classroom and I were to spray cologne up here in the front of the room, this is where the higher concentration is, and it will go to the lower concentration. So the person that would smell it last will be the person in the back of the classroom, because it's eventually diffusing out. It's mixing in with the other gases. And then effusion. You guys won't have to deal with effusion yet. Now I have one more PowerPoint here for you today that goes along with ideal gases. And how do ideal gases work? This is where we will do, with the ideal gases, we will do a little bit of math that is involved here. Let me get the slideshow going. Alright, so with ideal gases, we will have an equation that we talked about with ideal gases, and it will be PV equals nRT. Better yet, is known as the Pernert equation. PV equals nRT. Pressure and volume will be equal to the number of moles, the gas constant, and temperature. Now you see here on this first picture, as temperature goes up, pressure goes up. As temperature goes down, pressure goes down. So with this portion of this, we see that we have 100 kilopascals, which is a pressure, 300 Kelvin. Here, the temperature went up 300 to 600, so therefore if the temperature goes up according to this, temperature goes up, pressure must go up. 300 to 600, it doubled, so therefore the pressure must double. Eventually, if we continue to heat up that glass jar, this Erlenmeyer flask will bust. All right, and the molecules disperse out, and now the temperature is back dispersed, and we get back to equilibrium. So, kinetic energy is greater than its attractive forces. Gas molecules move freely and randomly in all directions. We kind of talked about this a little bit a while ago. You've got the liquid, here you've got the gas. A lot of kinetic energy going on with the gas versus the liquid. Gas molecule movement and temperature, the gas particles on the right have more kinetic energy than those on the left. So the gas on the right is at a higher temperature. You will see if you take chemistry next year that we will represent these kinetic energy molecule diagrams with arrows. The longer the arrow, obviously, the greater the kinetic energy it has. The shorter the arrow, the less the kinetic energy it will have. Elastic collisions. We're talking about elastic collisions. Elastic collisions, it says there's no net loss of kinetic energy. All I want you to think about here is if you have a water bottle. I'm looking for, I don't see one in here because nobody's been here. I don't have one. But if we take a water bottle and we tighten it up, and you take that water bottle, the pressure keeps building, and keeps building, and keeps building, and keeps building. Eventually, that water bottle feels like it wants to bust. Those molecules inside that water bottle, though, are constantly bouncing off the walls of the container. So that's what an elastic collision is. It's just simply where if I were to take this Diet Mountain Dew bottle, okay, and I were to tighten it, which it has liquid in it right now, so I can't compress it. It has the liquid in it. But if I were able to do that, those molecules inside this would be bouncing off those walls of the container. That's what an elastic collision is. So the more pressure, the more elastic collisions. The less pressure, the less the elastic collisions. Gases are going to take the shape of their containers. You see here we've got all kinds of different containers that go along here that have maybe helium in them, they have oxygen in them, they have petroleum in them, but we can put those gases in any certain type of container because they do not have a definite shape. Heavier gases may have lower kinetic energy. Once they get going, they may have the same kinetic energy as the lighter gases. So see how all lines eventually reach the same speed at that temperature. So here, it takes a whole lot of energy for oxygen to get moving compared to hydrogen because oxygen has a much heavier atomic mass. O2 is 32 grams. H2 is just 2 grams. So think about it that way. The lighter it is, the less work it's got to do. Okay? The heavier it is, the more work I've got to do. So I got to put more kinetic energy in to get it going. That one was on there twice. And that really gets us right there to begin to think about ideal gases. Now I'm going to pan over, and I do want to do one problem with you as we do these. Okay, let that focus. We talk about ideal gases. We talk about our ideal gas law equation. Is this PV equals nRT. P represents pressure, which for us, we can measure in atmospheres, we can measure in torr, or we can sometimes measure in kilopascals. We'll talk a little bit more about that later. Volume is V, which for us will be measured in liters or milliliters. N is the number of moles. We have talked about moles. We've converted some moles a little bit with you guys. R is a gas constant. And the gas constant that we will use if we're dealing with atoms or atmospheres, if we're dealing with torr, will be R is equal to 0.082 2, 1. Okay? That is the gas constant. This number will not change when we're dealing with atmospheres or torque. Okay? And that's what I'm going to give you on these problems right here. If you deal with kilopascals, that number R is going to be equal to 8.31. Okay? That is kilopascals. Because the number has to get greater, it gets greater because we went from kilo, and atmospheres we're not measuring in a much, kilopascals is going to be a much larger number. Alright, so there you go. Much larger number we're dealing with kilopascals, so therefore the gas constant is going to change. And it will be on the paper that I give you guys to be able to complete. And then after we do R, we've got T. T is going to be equal to temperature. Okay? And temperature has to be in Kelvin. And for us to put it in Kelvin, it's very, very simple. We can take, I'm gonna come over here, and for us to be able to convert to Kelvin, let's assume that we are given, let's just say 25 degrees Celsius, and we want to know what that is in Kelvin. All we have to do is take 273, take the degrees Celsius plus 273 plus degrees Celsius will equal K. So in this instance, 273 plus 25, we know is going to be equal to 298 Kelvin. When we talk about Kelvin, Kelvin does not have a degree symbol. All right, it is just the letter K. All right, so if you need to get into Kelvin, all you have to do is add 273 to it. So, knowing that is our equation, the equals in our table, we'll begin to talk about ideal gases and how these gases work. One other thing I want to talk with you about before is looking at some of these, and we'll look at some of these in next week's assignment and next week's lesson. We'll talk about pressure. One thing I do want you to know is if pressure goes up, temperature will go up. If pressure goes down, temperature will go down. These guys are directly proportional to one another. Okay, directly proportional. So if one goes up, the other must go up. If one goes down, the other must go down. We can have volume. If volume goes up, temperature will go up. If volume goes down, temperature will go down. Okay, you see pressure, temperature, volume, temperature. So they're on opposite sides of the equation. With the next one, all right, we can say that if pressure goes up, the number of moles will go up. If pressure then goes down, you assume the number of moles will go down. And vice versa. And this can keep going. And we'll talk about why pressure and volume are indirectly proportional to one another a little bit later on in the next lesson. So you see, these guys are directly proportional. Okay, now, as we do that, let's do one problem. I'm going to give you one problem. You're only going to have 6 problems that you have to do. I'm going to write the first one on the board here. If I have 4 moles of a gas at a pressure of 5.6 atmospheres and a volume of 12 liters, what is the temperature? So we want to do this just like we have done some of our other problems throughout the year. I want you to know that this is the equation you're going to use. So write down what each one of these are. Do we know the pressure? Do we know the volume? Do we know N? Do we know R? Do we know T? Okay? So, what is the temperature? So we know that's what we're looking for. Here, that is what we're looking for. We can underline that. Now, if I have 4 moles of a gas, this guy is given. We said a while ago, N was equal to 4 moles. Okay? At a pressure of 5.6 atmospheres. There's our pressure. And a volume of 12 liters. There's our volume. Do we know R? Yes, we do. We said earlier that R is equal to 0.0821. All right, is our gas constant because we're dealing with atmospheres. So therefore, we're looking for temperature. So we're going to plug this into our equation. Here's our equation, PV equals nRT, 5.6 atmospheres is our pressure. Our volume is 12 liters, is equal to N, which is 4 moles, which is equal to 0.0821, and then find the temperature. Okay? So that's what we've got. That's all we have to do. Now it's just a simple plug and chug. We put it in our calculator. We get T by itself. I'm just going to move this over. 4 moles, 0.0821. Move these guys over here. It gets T by itself. Now temperature equals, get my calculator, as I do this with you, we're going to do 5.6 times 12 equals 67.2. That's the top. 4 moles times 0.0821, that is 0.3284. Do our division here, 67.2 divided by 0.3284, we get a temperature that is equal to 204.6 Kelvin. And that's how you do these problems. You're only going to have 4 or 5 more to do, and I want you to work through these and work some of these ideal gas law problems. Now, that is it for today's lesson on how we're going to do gas laws with PV equals nRT. We'll expand on it a little bit more because we have Guy-Lussac's law, we'll have Charles' law, we have Boyle's law, we have all these different laws that go along with PV equals nRT. But here's the main thing. If you have a question, you need to make sure you ask me on Wednesday I will have a time set up, and I'm going to put this in Google Classroom for you. It'll be sometime after 10 o'clock. For you to get on there and ask me questions. If you have questions, a 30-minute segment. If you can't get on Zoom, email me, okay? If you can't do that, you can call my school phone. I'm here on Mondays from 9. I'll be here on Mondays from 9 to lunch. From 9 to 12 is what time I'll be here on Mondays. So you can call me then on the school phone. 4922 is my extension. So that's what we have. But just remember, don't get overwhelmed. If you have a question, ask. If you need something, tell somebody. It is more important, your health and your safety, than some of the other things that we're trying to do here. I know it's different. I know it's new. But hey, we're going to get through it and we'll defeat this thing. Appreciate it.